Okay, so in this video, we're going to be talking about adding or subtracting polynomials, and we're going to begin by actually defining what a monomial is. Once we do this, we're going to move into defining polynomials. We're going to look at the degree of the terms of each of these terms and polynomials themselves. Then we're going to evaluate polynomial functions, and finally add or subtract the polynomial functions. So the first thing we're looking at here is a monomial. Now, a monomial is going to be an algebraic expression with exactly one term, all right? In general, a monomial in one variable is a term of the form ax to the m, where a is constant and m is a whole number. So some examples of this could be something simple like 2x or 1/2 x to the fifth. You can also have more complex monomials. For example, how about negative 2/3, a to the fourth, b to the third, c to the ninth. And you can even have a monomial that looks like this, just the number 2, all right? Notice, though, each one of these only has one term, all right? Now, if we branch out a little bit, we end up getting what we call polynomials. So a polynomial is nothing more than two or more algebraic terms combined by, and this is the key right here, addition or subtraction, all right? So we can make a little note here at the very top. Terms are separated by a plus or a minus sign, okay? So for example here, we have a monomial, and we know a monomial has exactly one term. A binomial, just like a bicycle has two wheels, a binomial has exactly two terms. So it could look something like this. How about 3xy plus 2z? That's a binomial, okay? And then finally, you can have a trinomial, which has exactly three terms, and that could look something like this. 2x squared minus x plus 16, okay? All of these, though, no matter which way you look at it, are all polynomials. Anything with more than three terms, we just call it a polynomial, and that's it. All right? So now what we're going to do is we're going to learn how to define the degree of each term and the degree of the polynomial overall. Now I'm going to kind of do this backwards. So the degree of a polynomial is the highest degree of all of its terms. All right? Now, the degree of a constant is equal to 0. And then, and this is the one that students kind of mix up, the degree of a term is the sum of the exponents of its variables. So what you're going to do is you're going to look at the polynomial itself. You're going to find the degree of each term by adding up the exponents. So let me show you some examples of doing this. All right. So here's the first one here. We're going to find the degree of each term and then the degree of the polynomial overall. So for the letter y, that is a first degree. And the reason? The y is raised to the first power. For the constant -1, that is a 0 degree. And the reason for that? The degree of a constant is 0. So this overall is a first degree polynomial. Now, without going too far down the rabbit hole, that's actually extremely important for us because that first degree tells me how many solutions there are to this polynomial. It will tell me at most this is how many mins or maxes. It will also tell me about end behavior. I mean, there's so much information that just comes from the degree. Let's look at another one here. So how about 6mn to the third plus 2m to the second n to the fourth minus 8mn. Okay? So in each one of these scenarios, notice that we both have the variable m and n, and according to the definition of a term, or the degree of the term, you got to sum up the exponents. So I'll use a different color here underneath. So the m is raised to the first, the n is raised to the third. So this term is a fourth degree. Now the middle term, 2 plus 4 is 6. So this is a sixth degree. And then finally, the last term, the m and the n are both raised to the first power. So we would call this a second degree. Now, the polynomial, the degree of the polynomial here is going to be the highest degree of all of its terms. So that is going to be right here. So this is a sixth degree polynomial. Okay. Now the question becomes, all right, well, now that we understand degrees and everything, okay, how do we actually add or subtract polynomials? And the most beautiful part about this, you already know how to do that. So to add or subtract polynomials, it's just one thing. All you got to remember is how to combine like terms. And remember, just to review, to combine like terms, you need to be able to say yes to both criteria. The first, you want the same exponent. And the second, same variable. Now this isn't in order. You're just looking for same exponents, same variables. All right. So we'll do a couple here. All right. Nothing too crazy. So let's do this one right here. How about we'll use the word simplify. 3m to the second plus n to the second minus 7m to the second. Okay? Now, the one thing you can do is apply the commutative property. And what I mean by that is notice here, these two terms, and this is a trinomial, by the way, trinomial polynomial, these two terms have the same exact variable raised to the same exact exponent. So as long as I keep the sign in front of the number, the commutative property says you are allowed to rearrange them however you want. So what I'm going to do is put those two up front. And the only reason why I did that is so I can easily look at the two coefficients. 3 minus 7 is negative 4m to the second plus n to the second. And that's how you add or subtract polynomials. So I'll do one or two more here. And we're just going to make them like a little bit more complex. All right, nothing too crazy. So let's subtract. How about x to the second minus 7xy minus 3y to the second from x to the second plus y to the second. Now, the hardest part about this problem is just setting it up. We're subtracting the first polynomial, that's this, from the second polynomial, which is this, which means we have to rewrite this so that the second polynomial comes first, and then we subtract the first polynomial from that. Now, if you look at this, remember there's an imaginary positive 1 out front, and in between the two polynomials, this is a minus 1. So we're going to have to use our distributive property to remove the parentheses. So I get x squared plus y squared. And then for the second grouping, I get negative x squared plus 7xy plus 3y to the second. From here, all I have to do is look from left to right and kind of just see where my like terms are, kind of make a notification that they are like terms. So what I like to do is just, I like to underline things. So here's x squared, and there's minus x squared. So I know they're like terms. So if you wanted to, you can rewrite them right next to each other. Then here's y to the second, and here's y to the second. So I can write them next to each other. And finally, nothing groups with that positive 7xy, so I just put that off to the right-hand side. Now to simplify, x squared minus x squared, well, that cancels itself out. 1 plus 3 is going to be 4y to the second plus 7xy. Okay? And there is that example right here. So the only way that I can really make this more difficult is by giving you like more terms or more like terms to group. That's it. So now what I want us to do is I want us to look at a polynomial function. Now, if you remember, a function in general, and I'll write it above here, a function is a one-to-one correspondence that links each x value with exactly one y value. All right. In other words, for every x, you get exactly one y value. That is it. Okay. So when we talk about polynomial functions, they're nothing more than a function whose range of values are defined by a polynomial. So an example of this would look something like this, like f of x equals x squared minus x minus 6. That is a polynomial function where the variable x is our independent value. Whenever we substitute the value of x into the polynomial, the output, which we can think of as our y value, is going to be the range. Okay? So that's where this word comes in, the range of values. So we can easily do an example, and I'm going to use the same exact thing that we have here. So I'm just going to erase some stuff real quick. All right, so given, see if I can write that word in here. Given f of x equals x to the second minus x minus 6, evaluate f of 0 and f of negative 3. Okay? So directly underneath, I'm going to write part A, f of 0. Wherever I see the variable x, I put parentheses first. Then I'm going to make my substitution into the parentheses. So I put a 0 here and a 0 here. And therefore, f of 0 equals negative 6. Which means if I were to plot this on the rectangular coordinate system, I would plot the point 0, comma, negative 6. This is x, comma, f of x. That is the ordered pair. Now, let's go ahead. Let's do the second one. So f of negative 3. Remember, wherever we see the variable, we're going to put parentheses first. All right, I'll use a different color right here. So we make our substitution, and then we simplify going from left to right. So f of negative 3 is going to equal negative 3 to the second power is positive 9. Minus a negative 3 is really plus 3 minus 6. So f of negative 3 is going to equal 9 plus 3 is 12, and 12 minus 6 is 6. Therefore, the ordered pair will be negative 3, comma, positive 6. Okay? Now, polynomial functions really help us out when you think about trajectories. All right? So one of the things that we're going to learn, and I'm going to show you here right now. So we have this polynomial function, h of t equals negative 16 t to the second plus 150 gives the height of a stone t seconds after it is dropped from a 150 foot tall cliff. Find the height after t equals 0 seconds. Okay? So this polynomial function right here relates time in seconds to the height of the object. In other words, If you give me a time period, if you give me like a certain amount of seconds, I can tell you exactly where is this stone after it's dropped. Now, when you look at this, when we go to Desmos, I want you to see something real quick. So we'll go to Desmos. All right, and we're just going to type this in. Now, when you type in functions into Desmos, you don't have to worry about like the functional notation. We just want the relation. So this is going to be, I think it was, what was it, negative 16? Let me look at my notes again. Negative 16 t to the second plus 150. All right. So we get negative 16. And at Desmos, you have to use the variable x. So we get x to the second plus, all right, 150. And I'm going to make this look really, really nice. All right, so just give me 1 second here. So I like in fact, I like that in terms of what the picture looks like. It's the y-axis and the x-axis I got to kind of mess with a little bit. So let's make this 0. Actually, we'll make it negative 3. And we're going to go to 10. And then the y-axis, we're going to shrink this down a little bit. So we'll make it 0, and we'll only go to 175. Perfect. That looks beautiful. So what I'm going to do here is just copy and paste this into our notes. Whoops. All right. All right, that looks good there. And it's going to be huge, so I'm going to have to... There we go. That looks pretty good. Okay. So, please excuse my artistic ability. But what I'm going to do here is I'm just going to draw our building. So here's our building right here. All right. So we are standing at the very top of the building, and we have a rock, and as we drop the rock, time is going to progress, okay? And I'm going to be able to tell you at like 2 seconds, the rock is right there. At 1 second, at 1 second, the rock is right there. At 3 seconds, the rock is right there. So you can kind of see how this models exactly what's going to happen. And you can do this outside and model it the same exact way. All right? So, excuse me. So let's go ahead and let's evaluate what this wanted. All right? So they wanted the height of the object when t is equal to 0. That's right here. All right? We call this the initial height. So when you think about initial height, it makes complete sense. If you are standing there initially, the height should be 0. So we're going to go ahead, we're going to make our substitution. And negative 16 times 0 to the second, evaluate the exponent first. 0 to the second is 0. Negative 16 times 0 is 0. Our initial height is 150 feet, which makes absolute sense. Okay? Now, if we wanted to, like I said, we could take this a little bit further. For example, let's find the height after 2 seconds. Well, if you want to know the height after 2 seconds, all you have to do is substitute in 2 into the function, and then go ahead and evaluate. So remember, you got to do the exponent first. So 2 to the second is 4. 4 times negative 16 is negative 64. So let me write some of this out. So we get negative 64 plus 150. And when you take that, you get h of 2 equals 84 feet. So after 2 seconds, the rock is 84 feet. And if I kind of just erase some of this, right here at this point is 2, 84. And if I were to draw a line straight over, all right, it kind of looks like it's 84, all right, the height. And we can also see that if we look at 3 seconds, okay, so t equals 3, we can see that the rock is almost at the very bottom. We're looking right there. In fact, let me zoom in a little bit. Right here is 3. right there is the value right there. Okay? So, it's not perfect. It's not a perfect science, but you can definitely figure this stuff out. Okay? So now we're going to be talking about, well, if we have these polynomial functions, what are we allowed to do with them? And this is like the first real, I guess, introduction into adding and subtracting polynomial functions. You can do them exactly how you do anything else. In other words, for the functions f of x and g of x, you can add them together or you can subtract them together. So what I mean by that is this, all right? If f of x equals 3x to the second minus x plus 2, and g of x equals x squared plus x plus 1, let's find f plus g of x and f minus g of x. So notice there's two problems here, okay? And I'm going to do this a couple ways, and I just want you to see how this works, all right? So the first thing we're going to do, part A, is f plus g of x. Now, by definition, if you look directly above, and I'm going to highlight it for us, by definition, f plus g of x is equal to f of x plus g of x. So just like any other time when we substitute, we come directly underneath, we put parentheses first, okay? And then we make our substitutions. F of x is 3x to the second minus x plus 2. G of x is x to the second plus x plus 1. And then this turns into a very similar problem that we did earlier, which is adding or subtracting just regular polynomials. So f plus g of x is going to equal, well, remember, you got to distribute, but luckily for us, there's a plus 1 out front here and a plus 1 out front there. So we can just go ahead and remove these parentheses. Nothing is going to change. All right, when we go ahead and distribute the positives. So if I look from left to right, I get 3x squared plus x squared. Well, that's going to be 4x squared. Then we have negative x plus x. Well, that cancels. And then 2 plus 1 is 3. So there is f plus g of x, which is equal to 4x squared plus 3. It's the subtraction of these two that we need to be careful with, okay? So by definition, and I'm going to go back up so we can see it. By definition, f minus g of x is right here. And that means I can just rewrite these two functions and just put a minus sign in between. And that is where you got to be really, really careful, okay? So let's go ahead. Let's use a different color here. We're going to use blue. And I'm going to kind of make the marker a little bit thicker so we can see it. So there we go. So this is going to equal f of x minus g of x, okay? And to be honest with you, it wouldn't be a bad idea if you came up into your problem right here, okay? Sorry, I had like a little glitch here, so I had to pause the video real fast. But it wouldn't be a bad idea if you came up into here, and inside this definition, if you just kind of wrote brackets in there. And by doing that, you could put them down here as well. Okay? And that way, you will never, ever forget to put those parentheses, which is what we need. So, f of x minus g of x. F of x is defined as 3x squared minus x plus 2. G of x is x to the second plus x plus 1. And the first thing we got to do is go ahead and distribute this minus sign. So that's going to give us 3x squared minus x plus 2 minus x to the second minus x minus 1. So now, when we go ahead and we evaluate, f minus g of x, all we have to do is group like terms. 3x squared minus x squared, well, that's going to be 2x squared. Negative x minus x is going to be minus 2x. And then 2 minus 1 is plus 1. So that's what we have here. Now, there are other things we can do with this. For example, in part C, let's do f minus g of 2. Well, all this means is to first find, so let me write this here. So first, find f minus g of x, which we did. We just did that. It's 2x squared minus 2x plus 1, okay? And then second, evaluate. So all that means is f minus g of 2 is going to equal what we got our function, and then directly underneath, we put parentheses wherever we see the variable, and then we make our substitution. So I'm going to put a 2 here and a 2 there. And then we follow everything that we learned way back in the day, order of operations, all that stuff. So we get 2 to the second, which is 4, and 2 times 4 is 8. So this is going to be 8 minus 4 plus 1, and therefore f minus g of 2 is going to equal 8 minus 4 is 4, plus 1 is 5. Okay? So this would also be the point 2 comma 5, because your input is 2, your output is 5. All right? And I hope that made sense, because that is our first section all done. So I will see you in the next section, which we're going to go over properties of exponents and scientific notation. And this section is a biggie, because you're going to remember all your little rules for exponents from back in Math 90. So I'm going to go ahead, stop the video, and start doing the next one.